Hello everyone, this is Xiaojing Wang from Northwestern University. Now I'm going to share work I've sponsored a programmable dual-band metasurface for Sub-6 wireless networks. The work has been done by Northwestern University and the University at Buffalo. Next, we will talk about our motivation. As we all know, beamforming can improve the input throughput and extend the communication range. It's significant for scenarios that require high-speed data and complex environments. Recently, offloading the beamforming from the endpoints to a metasurface deployed in the environment has attracted attention, such as Lala, Fox, and SCAD-Memo. But they only focus on a single frequency band, 2.46 GHz or 5 GHz. In fact, concurrent wireless transmission over two sub-6 bands are very common. Let's take the family scene as an example. Smartboards works on 2.4 GHz ZigBee protocol, and monitors work on 2.4 GHz or 5 GHz Wi-Fi protocol. So, how to support beamforming for different frequencies and different protocols of IoT devices? A straightforward approach is to install two metasurfaces, one for a single band. However, it needs more deployment space and higher hardware costs. Another way is to design a new dual-band metasurface, such as stacking metasurface. Each layer works for a single frequency band. But the circuit design is very complicated. Another work uses Huygens principle to achieve dual-band beamforming, but use vectors to adjust phase, incurring high insertion loss and precise voltage control. To avoid the above issues, we introduce our work, F-bouncer. It can support concurrent beamforming on two sub-6 bands, and our metasurface is air-efficient, simple structure, and low cost. So how to design the metasurface? We have the following goals. The first, concurrent dual-band communication. The second, dual-band programmability. For the first, we face the challenge of discrepancy in electric length. The electric length of metal atoms depends on the operating frequency. Therefore, it's very difficult to achieve two widely separated frequencies in a fixed physical size. So we have two steps to solve the problem. The first step, fix the first resonant frequency at 2.4 GHz. The step 2, generate the second frequency at 5 GHz without affecting the first resonant frequency. The first step, we select the metal-backed patch square structure as our basic metal atom. We find the resonant frequency is determined by the length, the width, and the patch, and the height of the electric cuboid. So we use high-phase to simulate the impact of three parameters on resonant frequency. For example, reducing the patch length will increase the resonant frequency. By choosing the combination of parameters, we realize the resonant frequency is at 2.4 GHz. The second step is buried by the theory of slot antenna. We find that etching slots on the patch can generate the second resonant frequency. The final resonant frequency depends on the location and the number of the slots. According to our simulation results, we etch 4 slots at the edge of the patch. The optimized metal atom not only operates the two frequencies, but also measures the reflection efficiency. Then we need to empower programmability to metal atoms. Our solution is to use 2 pin diodes because of symbol control. From the figure, we can see that different states have the different phase shifts to signals. And the difference between each state is about pi/2 at 2 frequency bands. Thus, the finally metal term can be seen a 2-bit phase shifter. So how to achieve beamforming through F-bouncer? We start with single-band beamforming. We use a 2-element linear array as the example. The signal travels different distances before reaching 2 metal terms, results in incident phase difference. Similarly, the single departure also results in phase difference, which together cause the phase difference of the signals at the receiver. Therefore, to perform beamforming, each metal term should generate a compensation phase to remove the phase difference. Then we extend the binary linear array to a planary array and obtain the compensation phase in our metasurface. However, it's challenging to implement the phase shift of concurrent beamforming for 2 bands due to different incident direction, different departure direction, and different frequency. The phase shift of each metal term varies at 2 frequency bands. Our solution is to search for the combination of states of metal terms. We design the object function that maximizes the total gain of mean lobes, meanwhile ensure the fairness between 2 bands. From the figure, we can see that even though it can't achieve the best effect like a single band, but the dual band beamforming nicely matches the desired angle. Next, I will talk about how we implement our system. We make the prototype including 256 metal terms with a surface area of 35 by 35 square centimeters. To validate the performance of concurrent transmissions at 2.4 GHz and 5 GHz, we fix the transmitters working on the 2 frequency bands at different locations, and place the receivers at different locations. Then we move receivers at 9 different combinations of locations. We can see the F-bouncer can achieve an average SNI improvement of 9 decibels. This shows F-bouncer can work well for dual-band concurrent transmissions. We next study how F-bouncer performs when the user moves. We place the transmitter at a fixed location and move the receiver along the line with 2 speeds, slowly and normally. We can see the F-bouncer can consistently achieve SNI improvement at both different speeds and different frequency bands. Finally, we conduct an experiment in a real scenario. We place the receiver at 9 different locations, ranging from different elevation angle and azimuth angle and the height. We can see that almost all SNI improvements are above 2.5 decibels and up to 13.5 decibels. To conclude, in this work, we design a programmable dual-band metasurface, which can support concurrent beamforming over 2 sub-6 bands by a dual-band beamforming algorithm, and validate its performance in a wide range of practical scenarios. Thank you for your attention.